In this problem, we have a crate with mass of 20 kilogram and it's subjected to a varying force F. This force right here is a function of time, and the box sits on this surface, and we need to determine at what time it will start moving, sliding on the surface. We're given the coefficient of static friction between the crate and the surface, which is 0.15. So let's think about this situation. Initially, let's assume that this applied force is not big enough to cause this box to move. So initially, the frictional force developed is able to keep up with this increasing applied force. So the frictional force prevents the box from moving. Because the impending motion is to the right, therefore the frictional force is going to be to the left. But then at this critical moment, this is the instant when the frictional force has reached the maximum static friction. And this is when the box is about to start moving, and we need to solve for the time at that moment. So again, we start with the free body diagram. Box is subjected to its weight force, which is mg, that's 20 times 9.81 meter per second squared, because we're using SI units, and that is 196.2 Newton. The applied force is at an angle, 30-degree angle. Therefore, it can be resolved into two components. The horizontal component is F times cosine 30 degree, and the vertical component is F times sine 30 degree. Normal force, it is at a location that we do not know yet, and the frictional force tries to resist the impending motion to the right, therefore the frictional force is to the left. So when we're trying to solve for this moment, this is when the static equilibrium equations still apply. After this moment, after the box starts to move, after the box has acceleration, then static equilibrium equations will no longer apply. But at this moment, at this instant, the static equations still apply. Therefore, we can still write our resultant force along the x direction. That equals to F cosine 30 degree minus FF, and that equals to the 20 t squared plus 30 times cosine 30 degree minus FF, still 0. Resultant force along the y direction equals to, we have normal force minus the weight force, 196.2, minus the force, applied force vertical component, that is F sine 30 degree, so 20 t squared plus 30 times sine 30 degree, and that is also 0. However, if you look at these two equations, you realize that we actually have three unknowns. We have T, FF, and N, normal force. So in order to solve for all of these three unknowns, we need one more equation. But since we are given the condition that we're solving for the instant when the object is about to start moving, it does satisfy that the frictional force at this point is the maximum static frictional force, which can be evaluated by this equation mu Sn, which equals to 0.15 n, n being the normal force. So as you can see, now we have our third equation. Three equations, three unknowns, we can solve for all of them. So when we are solving for them, we'll probably first evaluate normal force from the second equation as a function of time. So from the second equation, normal force can be solved to be 10t squared plus 211.2. And then frictional force equals to 0.15 n, which equals to also a function of time, 1.5 t squared plus 31.68. And then from there, we substitute it into this equation for the first equation. So we have 20t squared plus 30 times cosine 30 degree minus 1.5t squared plus 31.68 equals to 0. So this is a quadratic equation with only one unknown. The only unknown is t. So from there, we just need to solve this quadratic equation. Not very difficult to solve. And we can solve for t to be 0.60 seconds. And that is the answer to this problem.